Hello, welcome to the SED lecture video. I am teacher Melay, and this is the continuation of our discussion on problem-solving heuristics. So we have the following heuristics. So we actually have A to letter K problem-solving heuristics. So we are done with A, B, C. So today, our focus is to modify the problem. So in the explaining this, we are going to solve this problem. So we are going to prove that there do not exist positive integers x, y, z such that x squared plus y squared plus z squared is equal to 2x, y, and z. So here we are going to modify the problem because as you can see, the value of 2x, y, z represents it represents an even number. So we know that by definitions, if n is equal to 2k, so this is in a form of even number, which means that if we let x, y, z be equal to k, then this is equal to even, or we can simply say that the sum of x squared plus y squared plus z squared is an even integer. Okay, so in the illustrating this, let us consider, let's have, as mentioned, we have x squared plus y squared plus z squared is equal to 2x y z. So we will simply modify this by saying that the result of the sum of x squared, y squared, and z squared is an even integer. But what we are proving here is it does that there will be no positive integer that will result to uneven integers. Okay, so we will let x be equal to x sub I or x sub 1, y is equal to 2y sub 1, z be equal to 2z sub 1, which represents that all our values are given. So we will consider different cases here. So the first one is we let x, y, and z be even integers. The second one, what if we have one odd number and two even integers? Number 3. So what if we have also 3 odd integer? And then number 4, if we have 2 odd and 1 even integer. Because in our given, so it is stated that there do not exist positive integers. Of course, even and odd integers or positive integers. So we are also going to see if what if the three variables x, y, z or even numbers, what if one is odd and two are even, what if all are odd numbers or odd integers, and what if we have two odd integers and one even. So for our first case, we will let x be equal to 2x sub 1, y be equal to 2y sub 1, and z be equal to 2z sub 1, which represents even number. So that's for case number 1. So by substituting it in our equation, it will be 2x sub 1 square plus 2y sub 1 square plus 2z sub 1 square, which will result to 4x sub 1 square plus 4y sub 1 square plus 2 z sub 4 rather z sub 1 square. And here we can actually bring out 4, and what is retained inside is x square y square plus z square, or x sub 1 square, y sub 1 square, and z sub 1 square. Now, in our original equation, it is written as 2x y z, and this is 4. Of course, we have to also rewrite this in a form of 2. So this can be written as 2 square x square y square plus z sub 1 square, which means that the result is even. So if our variables x, y, z are all even integers, then the result is even. So which means that there exists if all are even integers. Okay, now let us consider the second case. So for our second case, what if we have two odd integers and one even? So we are going to let x sub 1, or rather x, be equal to, so let us change this. So let x be equal to, odd is represented as 2x sub 1 plus 1. So by definition, if n is equal to 2k plus 1, it means that this is the form of odd integers. Okay, so we have 2. So let y be on odd integer also. So let us use 2y sub 1 plus 1. And z is equal to z sub 1. So it's an even integer. Substituting it in our original equation, so this will become 2x sub 1 plus 1 square plus 2y sub 1 plus 1 square plus, of course, we have 2z sub 1 square. So expanding this is 4x sub 1 square plus 4x sub 1 plus 2 plus we have 4y sub 1 square plus 4y plus 4y sub 1 plus 1 plus 4 sub z sub 1 square. Okay, so we can this is plus, let's go back here. This is plus 1. So it is 4x sub 1 square plus 4x sub 1 plus 1. So we can combine 1 plus 1. So that is, of course, 2. So if we combine this is plus 2. And then we can factor out 2. If we factor out 2, so we have 2x sub 1 square plus 2x sub 1 plus 2y sub 1 square plus 2y sub 1 plus 2z sub 1 square plus 1. 1 because we have 1 plus 1 is equal to 2. So if we factor out 2, then we have plus 1 retained inside. So which means this again yields to an even result. So if we have two odd integers and one even number or one even integer, the result is also even. So again, this confirm that there do not exist, because in the reality there exists. So we have proven that for first case, it is true. It is not true that there do not exist, because there exist when our variables x, y, z are all even. And we also prove here in this example that it is there also exists an even integer if we have two odd and one even. So let us still continue our cases. So let's consider case number 3. So in case number 3, we have three odd integers. So by substituting again or letting x sub 1 be equal to, rather by letting x be equal to 2x sub 1 plus 1 and y be equal to 2y sub 1 plus 1 and z be equal to 2z sub 1 plus 1. So by substituting this in our equation, so we have a result of course, 2x sub 1 plus 1 square plus 2y sub 1 plus 1 squared plus 2z sub 1 plus 1 squared. So doing the operation, this is 4x sub 1 plus 4x sub 1 plus 1 plus 4y sub 1 plus 4y sub 1 plus 1 plus 4z sub 1 plus, oops, this is actually 4x sub 1 square and 4y sub 1 square. And we have 4z sub 1 square plus 4z sub 1 plus it's 1. Okay? And then, of course, if we will add 1 plus 1 plus 1, it will be equal to 3, which means that we can just add 2 plus 1 plus 1 is equal to 2. So that our objective is, of course, to come up with a form of 2k plus 1. Because, of course, we cannot make it 2k because of the extra 1 or because 1 plus 1 plus 1 is an odd number. Okay, so by doing that, so this can be equal to, so we can actually again factor out 2. So what is left inside is 2x sub 1 square plus 2x sub 1 plus 1 plus 2 sub y sub 1 square plus 2y plus 2 sub z sub 1 square plus 2 sub z and then plus 1. Because of course, 1 plus 1 is equal to 2. So we have an extra 1 here because we have 1, 2, 3, 1. So we have an excess of plus 1. And this is not, of course, if we let this be equal to k, then this is in a form of 2k plus 1, which means the answer is an odd integer. So this is the case only that will show that there do not exist x, y, z if, of course, our x, y, z are odd integers. So the result is not 2x, y, z. Okay, let us continue. So what else did we not finish? So we're done with all three variables for even. The second one is 2 are odd, 1 is even, and then 3 are odd. So what if we have also 2 even and 1 odd? So let's have the last case, 2 even and 1 odd. So we let x be equal to 2x sub 1 plus 1. Oops, it's even. So it is just 2x sub 1 So let us continue. Y be equal to 2y sub 1 and z be equal to 2 sub z sub 1 plus 1. So it's an odd integer. So by substituting it in our equation again, this is equal to 2x sub 1 square plus 2y sub 1 square plus, so we have 2 sub z sub 1 plus 1 square. So answering this, so we have 4x sub 1 square plus 4y sub 1 square plus, so we have 4z sub 1 square plus 4z sub 1 plus 1. So we can factor out 2 raised to n for this, or 2 raised to 2 rather. And what is left inside is x sub 1 square plus y sub 1 square plus z sub 1 z sub 1 z sub 1 square plus z, but we have z sub 1 plus 1. So which means this is again in a form of an odd integer. So which means that there do not exist if we have two evens and odd. So let us make a summary for this. Okay, so for our case 1, when 3 or even, the result is even. And then for number 2, case 2, so 3 odds, the result is odd. And the last one is 2 or even plus 1 odd. So here 2 odd and 1 even. So the result here is even. 3 odds, the result is odd. The result is odd. So which means we will modify the problem dot instead of the original one. So it will be prove there exists, or rather there do not exist positive integers x, y, z with so we have actually here two cases with x, y, so let us modify that. With all prove there do not exist positive integers x, y, z if all are odd integers or at most one is odd, or at most two is even rather. at most 2 or even. Okay. So, prove there do not exist positive integers x, y, z if all are odd integers or at most 2 are even. And we can also write it as x squared plus y squared plus z squared is equal to 2n x, y, z. Because as you can see, when we factor out our 2, so it resulted to 2n, 2 raised to n x, y, z. So when we obtained a result of 2 raised to 2. Okay, so this is all for this video. Thank you for watching. So this example is an example of using or modifying the problem. Thank you for watching.